The problem from GATE Physics 2015 reads as follows. The band gap of an intrinsic semiconductor is Eg equal to 0.72 electron volts and mh star equal to 6 times me star, where mh star is the effective mass of holes and me star is the effective mass of electron. At 300 Kelvin, the Fermi level with respect to edge of valence band is. This is a numerical answer type questions, and we have to round off our answers to 3 decimal places, and the unit should be electron volt. The value of Boltzmann constant has been provided in the question itself. We'll have to use it. Now, just pay attention to the language used here. The Fermi level with respect to edge of the valence band. This implies we need to find EF minus EV. So we need to find this quantity, this numerical value in EV, because EG is also provided to us in EV. Now, this is the typical band diagram that we are habitual of seeing. So on the top you have EC, bottom you have EV, and the gap between them is called band gap. This is what we know as, and this has been provided in the question, EG. Note that this is an intrinsic semiconductor. Intrinsic semiconductor means there is no doping. Now, usually what we expect is that Fermi level should be exactly midway. So I have drawn this dashed blue line, EC plus EV by 2, to be exact midway. So we expect that this should be exact midway. But is it midway? We'll have to evaluate some expressions, and we'll see whether the EF coincides with this midpoint line or not. So let's go ahead. Now these are the typical expressions which you encounter. N is your electron concentration in conduction band, and this is the expression for that. For instance, similarly, holes in valence band, this is the expression, and these expressions have been obtained using, these are obtained using Fermi Dirac statistics. I'll provide a reference in the last slide, and you can refer it for more details. But anyways, this is the formula for that. So effectively, electron concentration depends on the difference of Fermi level and conduction band. Similarly, hole concentration depends on the difference, or exponentially depends rather, on the difference between valence band and Fermi level, and also on the temperature. And this is a constant, which again is temperature and effective mass dependent. Me, this is actually me star. So sorry for that. Yeah. However, we know that for an intrinsic semiconductor, now this is the case for an intrinsic. In intrinsic, we know that N equal to P. So this expression, NC E raised to the EF minus EC over KT, should be equal to the holes concentration in valence band, which is equal to NV e to the power. So I have taken minus common here, EV minus EF over KT. Now we solve this. We solve this expression, right? We just take NV over NC, and we just rearrange the terms here. So this is a simple algebra, and you get this expression, EF equal to EC plus EV by 2 plus KT over 2 natural log of NV over NC. NV and NC, the expressions are written here, and this is also known as the extrinsic. This is also known, this EI that you see here is nothing but intrinsic Fermi level. Intrinsic Fermi level. And if we place the value of NC and NV here, and we get this expression that you see at the bottom of your screen. Now note that this intrinsic Fermi level, so mid gap, we noticed that in the last slide, mid gap is exactly EC plus EV by 2. However, this intrinsic Fermi level, EF or EI, is slightly above it. Note that there is a slight deviation from the mid gap. So this is the slight deviation that I was talking about. It's not exactly at mid gap. It will be at mid gap only when the effective mass of holes is equal to effective mass of electrons, because then it will be natural log of 1, which is 0. So if effective masses are the same of electrons and holes, then and only then the intrinsic Fermi level lies at mid gap. Otherwise, it lies either slightly above or slightly below. We'll try to evaluate that, how much above for this question or how much below for this question. We'll evaluate that. Now, there's one catch here, that these expressions that I have written here are not always valid. These are valid, these so N and P expression, and based on this which we write the Fermi level expression, are valid only for non-degenerate semiconductors. Now what are degenerate semiconductors? Degenerate semiconductors are where they satisfy two conditions. First, EC minus EF must be greater than equal to 3 kT, and EF minus EV should be greater than equal to 3 kT. Or in other words, let's say this is EC, this is EV. I'll use a different color pen now. In this dash line, let's say this gap is 3 kT. This gap is 3 kT. Similarly, this gap is 3 kT. So Fermi level has to lie somewhere in between. So Fermi level can be anywhere here. If and only if the Fermi level lies somewhere in between this gap, then and only then these formulae are valid. Otherwise, these formulae are not valid. So only when Fermi level lies in this region and satisfies these two conditions, then and only then we have a non-degenerate semiconductor, and these formulae are valid. So in our question, we'll just go ahead and assume that it's a non-degenerate semiconductor, and in the last we'll verify that whether it's degenerate or non-degenerate. Now coming back to the problem, we were required to find EF minus EV. So I'll replace this expression for EF here. So it will be EC plus EV by 2 plus 3 kT by 4 natural log of MP star over Mn star. This is the first term, and we'll deduct minus EV because we have to find with respect to edge of valence band. So with respect to this, so I'll take EV this side, so it will be EC minus EV by 2. The second term remains the same, 3 kT by 4 ln MP star over Mn star. Now note that EC minus EV is nothing but EG. Note that EC minus EV, this is nothing but the band gap, the difference between conduction band and the valence band. So this will be EG by 2 plus 3 kT by 4 ln MP star over Mn star. Now we'll just plug the values. So EG is given as 0.72 by 2 plus 3. The value of K is 1.38 10 to the power minus 23 times temperature Kelvin, divide by 4 ln MP, it is nothing but Mh star is given 6 Me star. So I'll write 6 Me star, and this is Mn star. Mn star is nothing but effective mass of force. The other symbol is Me star. Right, now note that this kb unit is given as joules, so this will be in joules. However, the first term is electron volts, so the way to convert joule into electron volt is we simply divide it by 1.6 into 10 to the power minus 19. So what we'll get is 0.36 plus let's get this 3 by 4. Okay, this is kT, so this will be 0.026 electron volts times this is ln 6. So this will come out to be 0.36. Let me get my calculator. So it's 0.75 times 0.026 times ln 6, that's 0.035. okay, plus 0.035. so this will come out to be, if we add this, 0.395. okay, so note that I'll change my pen here for a second. Now note that the deviation from the mid gap is 0.035, right? 0.36 is the mid gap level, which is Eg by 2, right? However, above the band gap, so this EF rises 0.035 above the band gap. So if this was EC plus EV by 2, so our EF, I'll use green color, so our EF is somewhere here. This green color is EF, and the value of EF from EV we just calculated is 0.395 EV. right? And this mid band gap which we have already drawn, this is 0.36 eV, because this is halfway of 0.26. So our answer is, so we have got our answer in this case is simply 0.395. The units are already EV, so the units are EV. Now I told you we must verify whether this is non-degenerate or not. Remember, all this formula comes when it's non-degenerate. So let's verify whether this system is non-degenerate or not. So the way to verify is we first calculate EC minus EF. So EC minus EF means this gap. Now this gap, what is this gap? This gap is nothing but this gap is halfway. So if we deduct, so we can write it as EC minus EV minus EF minus EV. I am doing nothing but subtracting EV, because EV is a reference. EC minus EV is 0.72, EF minus EV is nothing but 0.395, right? So it will come out to be 0.72 minus 0.395 comes out to be 0.325. 0.325. And is it greater than 3 kT? 3 kT is nothing but 0.078 EV. So yes, 0.325 is greater than 0.078 EV. So first condition is satisfied. We are good here. Second, we need to check EF minus EV should be greater than or equal to 3 kT. So EF minus EV, we just calculated it. That's 0.395. So 0.395 EV is greater than or equal to 0.3 kT is 0.078 EV. So this condition is also true. Hence, our assumption that this system is non-degenerate is correct. And the formula that we applied is correct. So everything is correct. So our answer is also correct. So the answer that we found out was that the value of Fermi level with respect to edge of valence band is 0.395 electron volts. Thank you for listening.